Bismillah ar-Rahman ar-Rahim. In this video, we will discuss some examples of the magnetic circuits. But before discussing the examples, I would like to compare electric and the magnetic circuits. A electrical circuit is shown in front of you that is consisting of a voltage source and the resistance that is going to act as the load. So when you are going to connect the load with the source, a current is drawn by the load from the source, that is I. So we say that the current is going to flow in this loop. Okay, if you look at the magnetic circuit, it consists of a core that is shown over here, and you can see a winding over here in which the current is injected from the external source. When the current flows over here in the winding having n number of turns, a flux is established. The direction of the flux can be determined by applying the right hand rule, and that flux flows in this core structure. This core is made up of a magnetic material having the relative permeability mu r, and what is the permeability? Permeability is the ability of the material to allow the magnetic flux to pass through it. If its relative permeability is high, let's suppose 5000, that means that this material is 5000 times more permeable than the air. So permeability is given as mu naught into mu r, where mu r is the relative permeability and mu naught is the permeability of the free space or the air. So when we say a material has the relative permeability 5000, it means it is 5000 times more permeable than the air. It has the ability to allow the magnetic flux to pass through it, that is 5000 times more than the ability of the air or the free space. So most of the flux will flow through this core structure because it is of highly permeable material as compared to the air which is in the surrounding, right? So we say that most of our flux, rather all of our flux, is confined in the core structure and that passes through the core. In the electrical circuit, we have the resistance that depends upon the length of the circuit or this material and the cross sectional area through which the current is passing, and the resistance is given by this expression that it is equal to rho L over A. Similarly, in the magnetic circuits, the reluctance is basically the resistance that is offered to the flow of the flux. As over here, what is the resistance? That is the opposition to the flow of the current. Similarly, in the magnetic circuits, the opposition to the flow of the flux is called the reluctance. So how we can represent this magnetic circuit in terms of an equivalent circuit or the equivalent electrical circuit? So that is shown over here. Here this winding, which is going to act as the source of flux and giving you the MMF, magnetomotive force, that is equal to the product of the number of turns and the current. So that is modeled like this. This is like the voltage source in the electrical circuit. Over here it is EMF, electromotive force, that is the voltage source. Similarly, in the magnetic circuits, you have MMF, magnetomotive force, that is equal to Ni, and that is in the structure is basically this coil. The number of turns are N and the current that is passing through the coil is I. So the product of these two is going to give you the MMF, and that is modeled like that. And the next thing that you need to model, that is the resistance offered to the flow of the flux, that is the reluctance, and that depends upon the length of the structure through which the flux is going to pass. So the reluctance that is represented by this symbol is directly proportional to the length, and like the resistance, it is inversely proportional to the area, cross sectional area. So combining these two, we can write it like that, where mu is the permeability of the material that I have already discussed. So the reluctance is given by this expression, and the permeability is defined like that, that it is equal to mu naught into mu r. For any material, you will be having a relative permeability compared with the free space or the air. So you will be using this permeability and the cross sectional area through which the flux is passing, cross sectional area of the material, right? And then if you have only the air, let's suppose there is an air gap over here, right, like this. So the cross sectional area will remain same, but the permeability will be different in this region if there is an air over here. So if there is an air, you will calculate the reluctance with the help of this expression, that is length over mu naught A. The length is the length of this air gap through which the flux has to pass, cross sectional area, and the permeability of the free space. Sometimes we consider the fringing effect as well. What is the fringing? That is the spreading of magnetic lines of forces when they enter from one medium to the other medium. So in that case, the area of this air gap will be slightly higher than the area of the core, cross-sectional area of the core, usually 5% higher because of the spreading effect of the magnetic lines of forces. So if you consider the fringing effect, the cross-sectional area will be different. Otherwise, you can assume the same cross-sectional area as that of the core for the air. Okay, then if you look at the Ohm's law in the electrical circuit, that is V is equal to IR, and using that you can find out the current by knowing the information of voltage and the resistance. Similarly, in the magnetic circuit, there is the magnetic Ohm's law that is equal to that is defined by this one, that mmf is being represented by F. So that is the product of the flux and the reluctance. We have discussed it in detail in our theory class. So from here we can work out the flux. Flux is given as mmf by the reluctance, and mmf is Ni over R. So if you compare the two circuits, electrical and the magnetic circuits, so the current in this circuit is equivalent to the flux in this circuit, because when you apply voltage over here, the current flows, and when you apply mmf over here, the flux flows. So current and flux are analogous to each other, and similarly over here, resistance is analogous to the reluctance of this one, that is shown over here. So as the resistance opposes the current, similarly the reluctance opposes the flux. And over here the voltage source, over here is the mmf source. So you can develop one-to-one relationship between the parameters of the electrical and the magnetic circuits, and for that you can refer to the lecture in which we discuss the magnetic circuits in detail. Okay, now I am going to move towards the examples, solved examples related to the magnetic circuit. So a magnetic circuit is shown in front of you. It consists of a core structure that you can see over here, and this core structure has the relative permeability of 4000. It means 4000 times more permeable than the air, and the permeability of the free space is 4 pi into 10 raised power minus 7, and the cross sectional area of this core is 1 centimeter square. And we need to work out what will be the flux in this air gap. The length of this air gap is 3 mm, right? And the coil is shown over here. There are 500 turns in this one, and the 10 ampere current is being injected in this coil. Okay, so for the analysis of the magnetic circuits, we assume the linear operation first of all, and secondly we assume that these magnetic lines of forces will be moving at the mean distance. What do you mean by that one? Because if you look at the flux in this structure, some of the magnetic lines of forces will be closer to the inner boundaries, some of the magnetic lines of forces will be moving at the outer boundaries. So if you look at the distance that is traveled by a certain magnetic line, that will be different from line to line. The line which is passing on the outer periphery will be covering more distance compared to the line which is passing at the inner periphery. So in order to simplify our calculation, we will assume that the magnetic lines of forces are moving at the mean path, the mean or the average distance, that is the central distance in this case, in the core structure. Okay, so the outer diameter that is given to us, that is the 20 centimeter, and the inner diameter is given to us is the 18 centimeter, and we need to work out the mean diameter, that is the central path over here. So that will be 20 plus 18 by 2, the average of these two, so that is going to be 19 centimeters. So average dia is 19 centimeter over here, and to calculate the radius, that will be equal to 19 by 2, so that is going to be 9.5 centimeter. Remember one thing, that in the expression of the reluctance that we discussed earlier, that is L over mu A, this L must be in meters and this must be in the meter square, the standard units. So we are doing these calculations in centimeter, you will have to convert it into the meters. Okay, so now what will be the equivalent circuit? The first step to analyze the magnetic circuit is to draw its equivalent electrical circuit or the equivalent circuit representation. So first of all, we are going to represent this one as an MMF source, that is the product of N and I. So we know the number of tons over here. There are 500 tons, 10 ampere current. So we can work out what will be this magnetomotive force, and that will be 5000 ampere ton. That is considered as this unit. Basically, ampere is the unit and T is representing the number of tons over here. So MMF has the units ampere ton over here, and ton is a dimensionless quantity and only the dimension of current. So ampere ton will be used to represent the MMF. Okay, then our reluctance of this path, this core structure, that will be calculated as length of this part divided by the permeability of this path into the cross sectional area. So that is this one. I am going to call it the reluctance of the core, and then the reluctance of the air gap. So these two are in series because the flux will have to travel through this core and then through this air to complete its loop. So that's why these two reluctances are in series. So just applying the electrical circuit concept, the total reluctance will be the sum of the reluctance of the air and the core. So this will be the equivalent circuit, and in this now we can apply all the electrical laws, those we have studied, Ohm's law, magnetic Ohm's law, Kirchhoff current law. Kirchhoff current law in the magnetic domain will be the Kirchhoff flux law, because sum of all the flux at a particular node entering and leaving, their sum must be equal to 0. Like the electrical circuit, at a node the current entering and leaving must be same, all the currents. So their algebraic sum should be equal to 0. Similarly, the algebraic sum of the flux should be equal to 0, neglecting the leakage flux. Okay, so now after representing this circuit in the equivalent circuit form, now we are going to calculate the reluctances, and for reluctances we need to know about the length and the permeability and the area. So we have two materials over here. The first is this core material, and it is highly permeable. Relative permeability is 4000 times. So to work out the reluctance, we need to look at the distances of these, or the lengths of these materials. So as we already discussed, the average diameter is 19 centimeter, and average radius is 9.5 centimeter, that is 0.095 meter. And what will be the length of this path? This is the circular one, so the circumference, that is the 2 pi r, will be giving you the length, the average length, the mean length, and out of that you will have to subtract this air gap to find out the length of the core. So that's why you can see the 2 pi r, that's the circumference, minus 3 mm, that is the length of the air gap. So subtracting this, you will be getting the length of the core, and that is 0.594 meter, right? And then you will be calculating the reluctance of the core, because you know the length now from here, relative permeability, permeability of the air or free space, relative permeability, and the cross sectional area. Cross sectional area is given to us, that is 1 centimeter square, so that can be written as 1 into 10 raised power minus 4 meter square. 10 raised power minus 4 is to convert centimeter square into the meter square. So we will be taking that one, that's the free space permeability, relative permeability, and then the area in meter square, and this is the length in meter. So from here you can calculate the reluctance of the core structure. So after calculating the reluctance of this core structure, the next step is to calculate this reluctance of the air gap. So now let's calculate that one. So that you can see the length of the air gap is 3 mm, so 0.003 meter. And then using the same expression that we used earlier, length over mu naught into A, only mu naught over here, not the relative permeability, because the material over here is the air, right? So 4 pi into 10 raised power minus 7 permeability of the air. Cross sectional area is same because we are neglecting the fringing effect. The length, that is 0.0033 mm, is equivalent to 0.003 meter. So we have calculated the reluctance. Now from the equivalent circuit that we discussed over here, these two are in series, so total reluctance will be the sum of these two. So we are going to take the sum of these reluctances, core reluctance and the air reluctance. So this is going to be this one, and then applying the magnetic Ohm's law, that is that flux is equal to MMF over the total reluctance. You know about this MMF, right? You know about the total reluctance of this path, RT, that is equal to core plus air reluctance. So you can work out what will be the flux in this one. So 5000 is the MMF, 500 into 10, 5000, and then dividing it by the total reluctance, you will find out the flux that will be established in this structure, and that will be passing through this core as well as through this air gap and will be completing its loop. So that flux is 19.9 milliweber. So using the analogy between the electrical circuit and the magnetic circuits, you can analyze any magnetic circuits by applying all the electrical rules as it is over the magnetic circuits. So here is an example in which we have discussed at how we can find out the flux. Just draw the equivalent circuit like the electrical ones and then analyze by applying all the electrical laws. Okay, now here is the second example related to the magnetic circuits, relatively complex structure. It consists of a core that you can see over here. The core structure is shown over here, and then there is a winding on the central arm over here having n number of turns, and which are given to us. There are 1000 turns in this, and the current is being injected in this one to establish a magnetomotive force, and that will establish the flux, and that flux will be moving in this direction by applying the right hand rule, and from here it will be divided into two paths and depending upon the reluctances of these two, right. So the reluctance of this part and the reluctance of this path, flux will be divided in two parts. Okay, so relative permeability of this core material is 3000, and the permeability of the air is 4.10 raised power minus 7,000 tons. And what we need to do? We need to calculate the current. What will be the required current over here such that we get this flux density in the air gap. This is the air gap. So over here in this air gap of 2 mm, we need the flux density of 1.7 Weber per meter square. That's what we require. And the cross sectional area is given to us, that is 1 centimeter square. So neglecting the fringing effect, the cross sectional area of this air gap will also be same. So we need to establish this flux density, and for that we need to work out what should be the current over here. That's what we need to do in this example. Okay, so first of all, again we will look at the equivalent circuit, and then we will calculate the reluctances, and then by applying the electrical laws we will solve it. So that what should be the MMF over here, and to establish the flux, and from that MMF, because we know that MMF is the product of the turns and the current, we know the turns and that these are equal to 1000, we will work out what is the current, what is the required current. So first of all, let's sketch the equivalent circuit. So this will be modeled like that, at F is equal to Ni, this is the magnetomotive force. Okay, and then we will have to consider the mean distances. So you will have to consider the distance, this distance for the reluctance of the central arm, and this reluctance is represented as R naught over here. So in the central arm we have the magnetomotive force, and the reluctance of that arm, that will be calculated by looking at this distance, and this distance is equal to what is this? The total distance is given to you is 22 centimeter, and the inner distance is 20 centimeter. So average of these two is the 21 centimeter, right. So this distance will be 21 centimeter in the length. So 0.5 centimeter is to be left from here, and 0.5 centimeter from here is to be left to have the mean point, the central point over here, to look at this reluctance. So that will be calculated using this distance. Okay, then as the cross sectional area is same, so I will be combining this part and this part together, and I will be assuming that the flux will be having this reluctance. This can be combined together, that can be represented in a single reluctance. So that is represented as R2 over here. So that is the reluctance. The flux will be divided into two paths from here, one path of this reluctance, and that reluctance is shown over here, and then the reluctance of this air gap, that is in series over here of this path. And coming toward this side, we have the reluctance of this point, this structure, and then the reluctance of the air gap. So reluctance of the air gap B, and this is the reluctance that is shown over here, R1. Okay, so let's start the calculation of the reluctance from the central arm. For central arm, as we discussed just now, that this is the length, and this length is equal to 21 centimeter. So length, mean length of the central leg, that is 21 centimeter, and in terms of meter it is 0.21 meter. So the reluctance is length over mu r mu naught into cross section area. So length divided by mu r mu naught, and then the cross sectional area in meter square. So that's why you can see 10 raised to the power minus 4. So the reluctance of the central leg is calculated like this. This is the central leg. Okay, so we have calculated r naught. Okay, now let's move towards the calculation of the reluctance of the left side of the core. Okay, so left side of the core, let's look at the distances. The total distance is 33 centimeter, and I assume that it is right at the center. Right at the center, so dividing this distance into two parts, so 33 divided by 2, so this is going to be 16.5, and from this 16.5 you will have to leave this 0.5 centimeter to get the central point over here, because we need this distance. So this distance will be 16 centimeter, and similarly this distance will be 16 centimeter. Similarly, this distance over here will be 16 centimeter, and this distance will be 16 centimeter over here, right? And then with this 16 centimeter, what about this one? This will be 20. If I consider it overall, this overall distance is 21 centimeter. The average of this 22 centimeter and this 20, because we are going to look at the mean path. Okay, so for the left side, what are the total distance? 16 centimeter over here, 16 centimeter over here, and 21 centimeter. That's the total length. And out of that, I will have to subtract 1 mm for this air gap. Okay, so for the left side, 16 centimeter plus 21 centimeter, and then I am going to subtract 1 mm from that. So it must be in the meter. So convert it into meter, do this, and so you will get 0.529 meter as the net distance of the left side core. Of the core, the length of the core, and then we can find out the reluctance, length over mu naught mu r a. So length divided by mu r mu naught cross sectional area. So this is the reluctance of this left side part, that is equal to and this one r1, the reluctance of the core. Okay, then we calculate the reluctance of the right side. So over here the difference is that air gap is 2 mm, rest of the distances are same. This is 16 centimeter and 21 centimeter. So total length is this 16, 16 and 21, but out of that we will have to subtract 2 mm of the air gap. So the remaining length of the core is 0.528, and the reluctance according to this length divided by mu naught mu r, this is mu r, this is mu naught, and the cross sectional area. So this is the reluctance of the core on the right side. Okay, so we have calculated the reluctance of this side, we have calculated the reluctance of this side. Now we are going to work out the reluctance of this air gap over here. The length is 2 mm, so that is equal to 0.002 meter, and for reluctance, length over mu naught a, this is the length, this is mu naught, and the cross sectional area is assumed same as that of your core, neglecting the effect of the spread of the magnetic lines of forces, that is a fringing effect. If that will be there, you will have to increase this cross sectional area accordingly. Okay, so the reluctance of the air is calculated like that, and the unit of the reluctance is ampere ton per Weber. By applying the magnetic Ohm's law, it is equal to the magnetomotive force divided by the flux, and the unit of the flux is the Weber, and for this we use the ampere turn. So that's why for the reluctance is ampere turn per Weber. All the way in all the previous discussion, the reluctance was ampere turn per Weber. Okay, so now we calculate the reluctance of this air gap. So the length is 1 mm over here. So in meters, 0.001 meter. So length divided by mu naught into a. This is the area, this is mu naught, and this is length. And note that we are not using relative permeability over here, because this is the air, this is not certain material. The permeability of the material is defined in terms of a factor with respect to the air. Okay, so the permeability of the free space only. So we have calculated the reluctance of the air gap. Now taking all of that information all together, this magnetic circuit, this circuit can be represented like that: reluctance of the air gap, reluctance of this air gap, reluctance of this part of the core, and the reluctance of this part of the core is this one, and this central arm, and this is the magnetomotive force, Ni. Okay, so now what we need? Like the electrical circuit, in the electrical circuit the current flows, so in the magnetic circuit a flux will flow, that is phi 2 over here and phi 1 over here, and let's suppose that the total flux is phi, like the current in the electrical circuits. So what we need, that this flux should be such that this should establish the flux density of 1.7 Weber per meter square. That was given in the statement, right? So how you define, how you relate magnetic field with the flux, magnetic field density with the flux, that is defined as flux per unit area. So flux will be B into A. So this B is known to us that it should be 1.7 Weber per meter square into the area, cross sectional area is known 1 into 10 raised to power minus 4 meter square. So we need the flux over here, that should be equal to 1.7 into 10 raised to power minus 4 Weber. This is the flux that is required in this branch to establish the required flux density, right? Okay, now what should be the total current then? Because if we know about this total flux, you can work out what is the required magnetomotive force, and then you can work out, okay, we know the number of turns, what is the current. So now we apply the current deviation rule in the electrical circuit. If we assume all of these fluxes are the currents, so the current, this one I1, can be determined by applying the current deviation rule, that is the resistance or the reluctance of this path R1 plus RB divided by this path and this path, because these two are in parallel. This current will be divided in these two parts, so R1 plus RA plus R2 plus RB into this total current I, and in terms of flux this will be replaced by the reluctance, and this will be replaced by the flux. Okay, so from here if I work out for I will be equal to R1 plus RA plus R2 plus RB divided by this into I1. So you will get the total current, or in terms of magnetic circuit, the total flux. So that comes out to be, you know the reading of that one, that this must be this value 1.7 into 10 raised to power minus 4, and you know about all of these reluctances. So the current that will be required is 4.84 into 10 raised to power minus 4 over here, and this is analogous to the flux. So I should write that this is the total flux that will be required in this branch. Okay, so this is the flux that is required. It is 48.4 milliweber. Okay, so this is required from here. This is required from here, and now let's look at the equivalent reluctance that will be seen by this source. So these two are in series, these two are in series, and then they are in parallel. So taking the series combination of these and then taking the parallel, and then the resultant will be in series with R naught. So you can work out the equivalent reluctance. So equivalent reluctance, that is R1 plus RB in parallel with R2 plus RA, and then that will be in series with R naught. So the total equivalent reluctance seen by this source is this one. And now you know that for the magnetic circuit, this MMF, that is equal to Ni. So by applying the magnetic Ohm's law, that F is equal to flux into the reluctance. So it means that should be equal to Ni. So we have compared Ni with phi into R equivalent, and from we can work out what is the required current. I is equal to phi into equivalent reluctance divided by the number of turns. So you have calculated the net flux over here, that is this 148.4 milliweber. You know about the number of turns, those are given to us in the statement, and that is 1000 turns. 1000 turns are there in this winding. So taking that N, that is 1000, and you have calculated the reluctance over here, the net reluctance that will be seen by this source, because this will be injecting the flux looking at the total reluctance of the structure. So the current comes out to be 3.21 ampere. So it means that if you will be injecting 3.21 ampere current in this winding that we have seen over here, the current over here 3.21, if you will inject this current in this one, it has the 1000 turns, so it will give you a flux, and that flux will be divided into two parts, and this flux will be divided in such a way that this will give you the flux density of 1.7 Weber per meter square in this air gap, right? So if I conclude what we have discussed in this tutorial, that first of all, draw an equivalent circuit of the magnetic circuit in terms of reluctances, in terms of MMF source, and then calculate those reluctances looking at the mean distances of the core or the mean lengths of the core and or the distance over which the flux will be traveling, and then just apply the electrical laws, consider current as the flux or flux as the current because they are analogous to each other, voltage source as an MMF or MMF as the voltage source, and reluctance as the resistance, resistance as the reluctance, only the domains are different. And then applying the analogy, by applying the electrical circuit laws, you can solve it for electrical parameters, and those are analogous to the magnetic parameters. So you can directly write in terms of the magnetic parameters. So you can analyze any magnetic circuit with the help of these steps. The first step, that draw in its equivalent circuit. The second step, calculate the reluctances and the MMF and all the circuit parameters. And third step is applying the electrical laws, Kirchhoff voltage law, Ohm's law, whatsoever it is, and then solve it for the required quantity. So that's all from this video. Thank you very much.